Good afternoon, students. Good afternoon, students. Morning class, we are discussing the definitions about NP hard and NP complete. So, can you listen my voice now? So, if yes, type in the chat box.
Yes, ma'am.
Okay. Okay, sir. So, I am not recapping all the definitions. Just before closing what we have discussed, from there onwards I am starting. So decision problem means any problem whose solution or answer is yes or no, then we'll call that problem as decision problem. And example for that one is M coloring problem or Hamiltonian cycle, etc. So decision algorithm means an algorithm designed for a decision problem is termed as a decision algorithm. So whatever the algorithm we are designing for Hamiltonian cycle or M colorable problem, so those algorithms will be called as decision algorithm. Next, optimization problem means finding the best solution among all possible solutions. The best solution can be either minimum one or maximum one. It will depend upon the given cost function. And the algorithm designed for optimization problem is termed as a optimization algorithm. And the example for optimization problems are knapsack problem, job sequencing, single source shortest path, etc. Next, P. So P stands for the deterministic polynomial time. So it contains set of all decision problems, and these problems will be solved by deterministic algorithm in polynomial time. So next one is NP. NP stands for non-deterministic polynomial time. So and also it contains set of all decision problems, and these problems are solved by non-deterministic algorithm in polynomial time. So the difference between P and NP is that the definition will be same, similar only. Only the difference is that in P the problems will be solved by using deterministic algorithm, but in NP the problems will be solved by using non-deterministic algorithm. So before going to the definition of NP hard and NP complete, so we'll be seeing another two definitions. One is satisfiability. So satisfiability is nothing but we'll be taking a formula and we have to prove that the formula is true for some assignment of truth values to the variables present in the formula. So in order to construct a formula, so we'll see the construction. Let x1, x2, so on up to xn denotes Boolean variables. Xi bar denotes the negation of xi. So all this we have completed in morning class. That's why I'm going a little bit fast. Literal means it is either a variable or its negation. So formula in the propositional calculus is nothing but an expression. So formula is nothing but an expression that can be constructed using literals and operators. Operators are and are. So these are the examples for formula. So here, so a formula is in conjective normal form. So if and only if it is represented as and say. That means in between the classes, and symbol should be present, and in between the literals, R symbol should be present. So distinct to normal form is quite opposite to conjective normal form. So satisfiability problem is to determine if a formula is true for some assignment of truth values to the variables. So CNF satisfiability is nothing but the satisfiability problem for CNF formulas. That means we'll be taking the formula in CNF and we have to prove that the formula is true. That is nothing but CNF satisfiability. So morning we have seen these two examples. Here in the first example, so both these algorithms belongs to conjective normal form. Why? Because in the first example, so it contains two classes, one bracket, one class, and another bracket, another class. In between these two classes, C1 and C2, n symbol is there. So in between the classes, n symbol is there. So in the first class, two literals are there, x1, x2. In between the literals, the symbol used is r. And also in the second class, two literals are there. In between the literals, the symbol used is r. So therefore, the first formula is in CNF. Similarly, second one also, it contains three classes, C1, C2, C3. So in between the classes, the symbol used is n, and in between the literals, in each class, in between the literals, the symbol used is r. So both the formulas are in conjective normal form. So first we have to prove the first formula to be true. So now how many variables are there in the first formula? 2, x1, x2. So I am taking x1 equal to true and x2 equal to false. So x1 bar will be false, x2 bar will be true. So in order to prove C1 and C2 in the first example to be true, so C1 must be true. So C1 in C1 two literals are present, L1, L2, x1, x2. In between these two R symbol is present. That means any one can be true. So x1 is true, x2 is false. So true or false means we'll be getting the first one. First one, true or false means we'll be getting true only. True only. Next, second class, x1 bar means false, x2 bar means true. So false or true means we'll be getting the true only. We'll be getting true only. So false or true, we'll be getting the true only. So first one is true, second one is true. True and true. So it is true. First formula is evaluated to true. Next, if you see the second formula. So f equal to, so x1 value is true or x2 value is false. And second class, x1 bar is false or x2 bar is true and so x1 bar is false or x2 is false. So here true and false. So finally the formula evaluates to false. So here we will be taking, we have to take formulas which evaluates to true, not to false. So don't take blindly. So if you take blindly, some formulas may evaluate to false. Next, algorithm for satisfiability problem. Algorithm for satisfiability problem. So here the algorithm contains two variables, E, N, where E indicates the formula, and N is the total number of variables. Total number of variables in the formula. So this algorithm is designed by using non-deterministic. So non-deterministic means it must contain three functions. One is choice, second one is success, third one is failure. So here in the algorithm, first step is we will be randomly assigning true, false values to the variables present in the formula. So for I equal to 1 to n, xi equal to choice of true, false. So these two statements indicate we will be randomly assigning true or false values to the variables present in the formula. Next step. After that one, next step. So in the next step, so we have to check whether the formula evaluates to true or not. So if E of x1, x2, xn. So x1, x2, so on up to xn contains true or false values. We are evaluating the formula. So if the formula evaluates to true, then the algorithm should terminate successfully. That's right, then success. Suppose if the formula evaluates to false, then it should terminate unsuccessfully. That's why else failure. So this is the algorithm for satisfiability problem. Next, so before going to the NP hard, so first we will be seeing another definition, that is reducibility. So here the symbol for reducibility is alpha. So here we will be taking L1, L2. L1 and L2 be problems, and we will say that L1 reduces to L2. If and only if. So see here, L1 reduces to L2. if and only if there is a deterministic polynomial time algorithm to solve L1 that solves L2 in polynomial time. So here, when we will say that L1 reduces to L2, so if there is a deterministic polynomial time algorithm that solves L1, so which already solves L2 in polynomial time, then we will say that L1 reduces to L2. And see here, we will be seeing the transitive. If L1 reduces to L2 and L2 reduces to L3, if you apply transitive, then we will get the L1 reduces L3. Then we will get L1 reduces L3. L3. So next, Hooke's theorem. Next one is Hooke's theorem. So satisfiability. So this is a theorem statement. So after completing the definitions of NP-hard and NP-complete, we'll come to the proof of Hooke's theorem. NP. So first see the statement. Satisfiability is NP if and only if P equal to NP. Satisfiability is NP. So this condition will be true if and only if P equal to NP. P means deterministic polynomial time. NP means non-deterministic polynomial time. Non-deterministic polynomial time. Now we will come to the definition for NP hard. So a problem, any problem L is NP hard if and only if it satisfies this condition. Satisfiability reduces L. A problem L is NP hard. So if it satisfies the condition, satisfiability reduces L. Satisfiability reduces L. So just listen the definitions. When we go to the problem, then you will actually understand what is reducibility reduces to L and how can we say that the problem is NP hard. Just remember these definitions. NP hard means so satisfiability reduces to L. If the condition is true, then we can say that the problem L is NP hard. Next, NP complete. So when can we say that a problem is NP complete? So if the problem is NP hard and it belongs to NP So we can say that a problem L is NP complete if L is NP hard and it belongs to NP. Then we can say that the problem is NP complete. So next we will see the relationship between P, NP hard and NP complete. So this one is the relationship between P, NP hard and NP complete. So P is subject to NP. And NP complete means it should belong to NP and it also NP hard. So morning class I already told you all NP complete problems are NP hard, but only few hard problems are NP complete. See here the intersection of NP and NP hard is nothing but the NP complete. So P is subset to NP. So here C means complete, NP complete. So NP complete problems are all NP complete problems are NP hard and very few hard problems are NP complete. This is the relationship between P, NP hard and NP complete. Next, we'll discuss about the Cook's theorem. Cook's theorem. So here the theorem statement is that so satisfiability is NP if and only if P is equal to NP. Satisfiability is NP if and only if P equal to NP. So in order to prove this, so we have to show how to obtain from any polynomial type non-deterministic algorithm A and input I, a formula Q, such that the formula Q is satisfiable if and only if the algorithm A has successful termination with the input I. So in order to prove the theorem, so first we have to show how to obtain from any polynomial type non-deterministic algorithm A and input I formula Q such that Q is satisfiable if and only if the algorithm has successful termination with the input I. Suppose if the length of the input I is n, if the length of the input I is n and the time complexity of the algorithm is small p of n. So where small p, that means for constructing the input I, the time required. So for not constructing the input, constructing the algorithm A, the time complexity is P of n. So where P is some polynomial. Then for constructing the formula Q is order of P cube of n into log n. It is approximately order of P power 4 of n. But this is all theory, so you need not worry. So, and the time needed to construct the formula Q is also order of P cube of n into log n, which is approximately equal to order of P power 4 of n. So this is about the non-deterministic algorithm. So first we'll be taking a non-deterministic algorithm and input I and formula Q such that formula is satisfiable if and only if A has successful termination with input I. So first we'll be taking the non-deterministic algorithm. After that we'll be taking the deterministic algorithm. So if the length of the I is n and time complexity of A is P of n, then the length of Q is the order of P power 4 of n, and the time needed to construct the formula is also order of P power 4 of n. So now we'll come into the deterministic algorithm. So deterministic algorithm Z is used to determine the outcome of A. A means non-deterministic algorithm. On any input I can be easily obtained. So the deterministic algorithm Z simply computes the formula and then uses a deterministic algorithm for the satisfiability problem to determine whether Q is satisfiable. So satisfiability problem is nothing but so we'll be taking the formula and we have to prove that the formula is true. So if order of Q of m is the time needed to determine whether a formula of length m is satisfiable, then the time complexity of Z is order of P cube of n into log n plus Q of P cube of n into log n. So this is the time required for the deterministic algorithm Z. Z. Next, if satisfiability is in P, then Q of M is a polynomial function of M. So Q of M is nothing but a polynomial function of M, and the time complexity of Z becomes big O of order of R of N, where R is some polynomial, So therefore, if satisfiability is in P, the condition is true. If the satisfiability is NP, then for every non-deterministic algorithm A in NP, so we can obtain a deterministic algorithm Z in P. So if the condition is true, satisfiability is in P, then for every non-deterministic algorithm A in NP, so we can obtain a deterministic algorithm Z in P. So therefore, the above construction shows that if the satisfiability is NP, then we can say that P equal to NP. So this is the theorem proof. This is not complete proof. This one is a partial proof. So how to take algorithms and how to construct the formula. So all our assumptions are given in your textbook. So once go through the textbook. So at the end, if time is permitted, we'll again discuss this theorem at the end. So simply what we have to remember means theorem statement is satisfiability is NP if and only if P equal to NP. So we'll be taking two algorithms. One is non-deterministic algorithm, another one is deterministic algorithm. For both the algorithms, the input and the formula is same only. And the time complexity is also given for constructing the formula and also for checking whether A is satisfiable or not, and also deterministic algorithm is Z for checking whether Z is satisfied, whether Q is satisfiable with the help of the deterministic algorithm or not. Here also the time complexity is given. So therefore, if the satisfiability is NP, then we will say that for every non-deterministic algorithm A in NP, we can obtain deterministic algorithm Z in P. So if the condition is true, then we can say that the P equal to NP. So now we'll see the differences between NP hard and NP complete. NP hard and NP complete. So NP hard problems can be solved if and only if there is a NP complete problem. If and only if there is a NP complete problem can be reducible into X in polynomial type. So in the morning class I already told you. So NP hard problems has the property that all other NP complete problems can be solved in polynomial type. So NP complete means can be solved by deterministic algorithm in polynomial type. Next, to solve any NP hard problem, it must be an NP problem. So, but in order to solve NP complete problem, it must be both NP and NP hard problem. So next, another difference is that so NP hard need not be a decision problem. But NP complete means it must be exclusively decision problem. Some examples that belongs to NP hard, NP complete. Examples are halting problem, vertex cover problem, circuit satisfiability problem, etc. And NP complete problems are so determine whether a graph is, that means nothing but a Hamiltonian circle, satisfiability problem, M coloring problem, etc. So if you want to note down the difference, you can note down. I give 2 minutes time. Next. So before moving to the NP-hard graph problems, so we'll see why halting problem is NP-hard problem. Why it is not NP-complete. NP-complete. So in order to prove any problem is NP-hard, the condition is satisfiability reduces that problem. Satisfiability reduces that problem. Satisfiability reduces that problem. So if this condition is true, then we can say that the problem is NP-hard. NP-hard. So in order to prove this theorem, first we'll construct an algorithm A whose input is a formula. Whose input is a propositional formula X. And suppose this X has n variables. X has n variables. And this algorithm, so all these n are Boolean variables. And algorithm A tries out all 2 power n possible truth assignments and verifies if X is satisfiable. If X is satisfiable. So if it is satisfiable, then we can say that the problem is NP-hard. And also this halting problem is undecidable. Undecidable. So it is undecidable, that's why no algorithm exists for this problem. So that's why it is not in NP. So since no algorithm exists for this problem, so therefore it is not NP. So that's why this problem is not NP-complete. 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 So if the problem belongs to NP and it is NP-hard, then we can say that it is NP-complete. Otherwise, it will be only NP-hard. Only NP-hard. Next, we will be discussing about NP-hard graph problems. NP-hard graph problems. In NP-hard graph problems, we will be discussing 3 problems. One is click decision problem. Second one is node cover decision problem. Third one is AND/OR graph decision problem. So before going to these 3 problems, first we will see the introduction. So in order to show a problem to be NP-hard, so we have to follow these 4 steps. We have to follow these 4 steps. Suppose a problem L2 is NP-hard, we have to show L2 is NP-hard. NP-hard. Then we have to follow these 4 steps. So step 1, what is the first step means? We have to pick a problem that is already NP-hard, already known to be NP-hard. So first we have to take a problem that is already known to be NP-hard. So NP-hard means, that means it is satisfying the condition satisfiability reduces L1. So this is equation 1. Satisfiability reduces L1. So first step is we are taking a problem that is already known to be NP-hard. That means it is satisfying this condition. Satisfiability reduces L1. Next, in the second step, we show how to obtain an instance I dash of L2 from any instance I of L1. That means from L1 instance we are obtaining the instance to L2 such that from the solution of I dash we can determine the solution to the instance I of L1. That means, so first we are obtaining the instance to L2 from L1 instance such that from the solution of L2 instance, if we can obtain solution to L1 instance. L1 instance. So this step 2 can be written in figure like this. How reduction of L1 to L2. So here I polynomial time transformation. So here from L1 instance we are obtaining the L2 instance, and next we are obtaining using the solution of L2 instance we are obtaining the solution for L1 instance. L1 instance. So this figure is nothing but a reduction of L2 to not L2, L1 to L2. L1 to L2. So from step 2, we can conclude that L1 reduces to L2. From step 2, L1 reduces to L2. This is equation 2. Equation 2. So in the last step, we will be concluding from 1 and 3. Step 1 and step 3 by applying transitivity. First equation is satisfiability reduces L1. Second equation is L1 reduces to L2. So therefore we will be getting satisfiability reduces to L2. If the condition is true, then we can say that L2 is NP hard. So how we got means by applying transitivity to equation 1 and equation 2. Then we will get satisfiability reduces to L2. If the condition is true, then we can say that the problem is NP hard. So equation is first equation is nothing but satisfiability reduces L1. How we got that equation means first we are taking a problem that is already NP hard. That means it is satisfied with this condition. So next, second equation, L1 reduces to L2. How we got this equation means, so from L1 instance, we are obtaining L2 instance, and from the solution of L2 instance, we are obtaining the solution to L1. If conditions are satisfied, then we can say that L1 reduces to L2. So if you apply transitivity to both these statements, then we will be getting the satisfiability reduces to L2. Therefore, L2 is NP hard. L2 is NP hard. So now we'll be moving to the problems. First one is the fifth decision problem. So we have to show that the fifth decision problem is NP hard. So the name itself indicates hard. So these are the hardest problems. So we have to prove that the fifth decision problem is NP hard. So before proving fifth decision problem is NP hard, so first you know what is the click. What is click? So click is nothing but a maximal complete subgraph of a given graph. Click is nothing but a maximal complete. Click is nothing but a maximal complete. The subgraph should be complete and it must be maximum of a given graph. and the size of the click is the number of vertices in it, and the size of the click is the number of vertices in it. If we take example. So for this graph, so what is the maximal complete subgraph? Can anyone type in the chat box? For this graph, what is the maximal complete subgraph? Maximal complete subgraph. Three. Okay, good. Now all of you listen carefully. So in your exam, either graph will be given, and you have to find the click for the given graph. Click is nothing but the maximal complete subgraph. So here this graph contains 4 vertices and 5 edges. So the maximal complete is 1, 2, 3. This is one subgraph which is complete. Why? Because it contains loop. Every pair of vertices contains an edge. Next, another one is 2, 3, 4. So this is another subgraph which is complete. So both these subgraph contains total how many vertices? 3. So click size equal to 3. So number of vertices. Size equal to 3. Next, we have to prove the click decision problem. We have to prove click decision problem is NP hard. Click decision problem. So shortcut for click decision problem is CDP. Click decision problem is NP hard. So how to prove this problem to be NP hard means, so first we'll be taking one theorem, and in the theorem we have to satisfy the theorem. How will we satisfy means we'll be taking one formula, and for that formula we'll be constructing graph. For that graph, if it has a click of size at least k, where k is the total number of classes in the formula, then the theorem will be satisfied. If the theorem is satisfied means we'll be taking one statement in Cook's theorem. With the help of those two statements, theorem statement and Cook's theorem statement, we'll prove that the click decision problem is NP hard. So all of you note down simultaneously. So theorem. So theorem is nothing but CNF satisfiability. CNF satisfiability reduces click decision problem. CNF satisfiability reduces click decision problem. So in order to prove the theorem, proof. So CNF satisfiability means we have to take the formula in CNF. Let capital F equal to end CI be the formula in CNF. So first we will be taking the formula in CNF and let x1, x2, so on up to xn be the Boolean variables in CNF in F. So x1 to xn be the variables in the formula. Next, after taking the formula, next we have to construct the graph for that formula. So we will show how to construct a graph G from formula F such that G has click of size at least means greater than or equal to k if and only if formula is satisfied. So if the taken formula is satisfiable, then the graph will be having the click of size at least k. So how the formula is satisfiable? So by assigning true, false values to the variables present in the formula, and we have to evaluate that formula. So if the formula evaluated to be true, then the graph will contain the click of size at least k. So now we'll see. So how to construct the graph? How to construct the graph? So for any formula F, so G equal to B comma E is defined as follows. So the constructed graph will contain vertices and edges like this. B equal to sigma comma I. So here the vertex will be represented like this. Sigma comma I, where sigma is a literal in class CA. So don't worry, we'll be taking one formula example, then you will understand. So what is this theory? So next, edges. So E equal to, when there will be an edge between two vertices, so if both the literals doesn't belongs to the same variable and the same class. Sigma comma I comma delta comma J. So both should not be belongs to the same class, I not equal to J. So here this condition for same class and so both the literals should not belongs to same variable. So this condition is for same variable. So here so we have to prove the click decision problem is NP-hard. How to prove the problem is NP-hard means first we have to satisfy the theorem. So in order to satisfy the theorem, first we will be taking the formula in conjective normal form. For that formula, so we will be constructing a graph and we will be checking whether that graph has click of size at least k or not. So when it will have click of size at least k, if and only if f is satisfiable. That means if the formula evaluates to true, then compulsory the graph will contain click of size at least k. At least k. So for constructing the graph, so edges will be represented like this: sigma comma I, where sigma is a literal in Ci. So and there will be an edge between the two vertices if both the vertices doesn't belong to same class and same variable, then only edge will be constructed between the vertices. So now we'll see an example, then we'll have a clear understanding. So example, f equal to x1 or x2 or x3 and x1 bar or x2 bar or x3 bar. x3 bar. So first we are taking formula, and for this formula we have to construct the graph. So before constructing graph, first we'll check whether this formula evaluates to true or not. True or not. So here first square bracket belongs to first class, second square bracket belongs to second. So in order to evaluate the formula to true, C1 and C2 must be true. C1 and C2 must be true. Must be true. So type in the chart box how many variables are there in the formula. Variables. How many total variables are there in the formula? 3 variables, x1, x2 and x3. Good. 3 variables. So now x1 equal to x2 equal to x3 equal to. So I am taking x1 equal to true. x1 bar will be false. False. x2 I am taking false. x2 bar true. x3. So for x3 you can take either true or false. Either true or false. Anything. I am taking false only. So x3 bar is true. True. So now check whether the formula evaluates to true or not. Type it in the chat box. First check C1. C1. Next C2. C1. So what is C1? So C1 contains x1. What is x1 value? True. R. So x2. What is x2? False. R. What is x3? False. So true or false means it evaluates to true. Next C2. C2. So x1 bar false or x2 bar true or x3 bar. So C1 and C2 are true. So f equal to true and true. So it evaluates. That means so we can construct a graph which will be having click of size at least k. So k means total number of classes. Here in this formula only 2 classes are there. So k value is 2. K equal to 2. K is nothing but the number of classes. Number of classes in F. Formula F. Formula F. So this formula is evaluating to true. That's why we'll be constructing graph and it will have click of size at least 2. We'll see another example also which evaluates to false and which doesn't contain click of size at least k. So first we'll see this one, then we'll go for the next example. So now we have to construct the graph. So for constructing graph, I already told you. So how vertices will be denoted, and so how to construct edges. See, so vertices means sigma comma I, where sigma is a literal in class CA. Class CA. See, in the first class, three literals are there: x1, x2, x3. So all of you listen carefully. So in your exam, like this, either graph will be given, you have to find the click, or else you will be given formula, you have to evaluate to do, or else you have to take the formula and you have to construct graph and you have to prove that the problem is NP hard. So here, so the first class C1 contains three letters: x1, x2, x3. So left side I am putting three dots. Three dots. Why? Because the first class contains three letters. First one is represented like this: x1, comma 1. 1. So where x1 is the literal, x1 is the literal, 1 is the class. 1 is the class. Next, second dot represents, what is the second literal? x2, and belongs to which class? First class. So x2 comma 1. Next, third dot indicates x3 comma 1. So third literal is x3 and this literal belongs to the first class. Have you understood? So how I have written the vertex in the graph G. So if you have understood that, then I will move to the next class. So first class contains three literals. So that's why left side I have put three dots. So first dot is for first literal, second dot is for second literal, third dot is for third literal. First literal is x1 and it belongs to first class. So x1 comma 1. No, second one, x2 comma 1. Next, x3 comma 1. Next, second class. For second class, I am writing the right side. So second class also contains three literals. I am putting three dots. Three dots. So first one. So what is the first one? In the second class, x1 bar. So x1 bar comma 2. It belongs to second class. Next, in the second class, what is the second letter? x2 bar comma 2. Next, what is the third letter? x3 bar comma 2. So the total formula F contains 6 literals. That's why the graph contains 6 variables. So left side I have taken 3 vertices and right side I have taken 3 vertices. Type in the chart box. So if you have understood the vertices, then I will go for the edges. How to construct edges between the vertices. Okay. So now for constructing the edges, so what is the condition? So both the literals should not belong to the same class and the same variable. Literals should not belong to the same class and the same variable. Then only there will be an edge between the two vertices. Now, see here, 6 vertices are there. So for shortcut, I am writing the first one, I am denoting it as 1. Second one, I am denoting it as 2. Third one, I am denoting it as 3. Next, fourth one with 4. Fifth one with 5. Next, sixth one with 6. Now, can we construct edge between 1 and 2? Can we construct between 1 and 2 vertices? 1 and 2 vertices. So here one student asked how k equal to 2. So k equal to 2 means number of classes in the formula. So here F contains 2 classes. See, first is bracket 1 class, second bracket another class. In between the classes, the symbol used is end. So 2 classes. That's why k equal to 2. and each class contains some literals. In between the literals, the symbol used is R. If you take any class which contains literals and the symbol used in between the literals is R. So here two classes, that's why K equal to 2. K equal to 2. So now, so the total formula contains six literals. That's why the graph will contain 6 variables. So first class contains 3 literals. That's why left side I have taken 3 dots. And second class contains 3 literals. That's why right side I have taken 3 dots. So first vertex. How we are representing the literal comma class. So what is the first literal in the first class? X1. And it belongs to which class? The first class. That's why X1 comma 1. Next, second letter, X2 comma 1. Third letter, X3 comma 1. Next, second class, X1 bar. X1 bar comma, it belongs to second class. That's why it is 2. Next, second literal in the second class, X2 bar comma 2. Next, third letter, X3 bar comma 2. So like this, we'll be writing the vertices in the graph. Next, we need to construct the edges between the vertices. We have to construct the edges between the vertices. Now we'll see. Can we construct edge between 1 and 2? Type it in the chart box. Can we construct edge between 1 and 2? 1 and 2. So here, if you see here, literal, in the first vertex, literal is X1. In the second vertex, literal is X2. Both are different. But if you see the class, 1 and 1. So if it belongs to same class, we will not construct. That's why 1 to 2, there will be no edge. 1 to 2. 1 to 2, no edge. No edge. Because they belong to same letter. Because they belong to same class, not variable, same class. Same class. So we cannot construct edge between 1 and 2. Why? Because classes are same. Similarly, 1 to 3 also will not construct. 1 to 3 also will not construct. Why? Because classes are same. 1, 3 also will not construct. Because classes are same. See here, second one, 1 1. Next, 1 to 4. 1 with every variable you have to check. Similarly, 2 with every variable. Similarly, 3 with every variable. 4 with every variable. 5 with every variable. And 6 with all other variables like that. So I'm starting with 1. So we cannot construct with 1 and 1 to 2 and 1 to 3. Why? Because same class. Next, 1 to 4. Can we construct 1 to 4? See here. Here class, in 1 it is 1, in 4 it is 2. But x1 bar belongs to same variable or different variable. X1 and x1 bar belongs to same variable or different variable. X1 and x1 bar belongs to same or different variables. So can anyone type it in the chat box? So same variable. So therefore 1 to 4 also no edge. 1 to 4 also no edge. Why? Because so x1 and x1 bar belongs to same variable. So 1 to 4 no edge because same variable. So now we'll check with 1 and 5. So literals are different, classes also different. So we can construct 1 to 5. Next, 1 to 6. Next, 1 to 6. We'll be checking that. So literals are different, classes also different. So we'll construct 1 to 6. So 1 to 5 and 1 to 6. We'll be constructing the edge. Why? Because means here Here, both the literals belongs to different variables and different classes. Different variables and different classes. That's why. So we'll be constructing edge between 1 to 5, 1 to 6. So from 1 it is completed. Next we'll start with the 2. 2 to 1, 2 to 3. Can we construct edge? 2 to 1. Can we construct edge? Can anyone type it in the chat box? 2 to 1. Can we construct edge? No. No is correct. Why? Because same class. 1, 1. So 2 to 1 there will be no edge. Similarly 2 to 3 also no edge. Why? Because same class. Same class. See. 1, 1. 1, 1. Next. 2 to 4. 2 to 4. Can we construct edge between 2 and 4? 2 and 4. Can anyone type it in the chat box? 2 to 4. So here x2, here it is x1 bar. Both belongs to different variables. Here the class is 1, here it is 2, different. So we can construct 2 to 4. 2 to 4 we can construct. Next, 2 to 5. Can we construct 2 to 5? No. Why? Because classes are different, but both the literals belongs to same variable. So x2 bar belongs to same variable. That's why there will be no edge between 2 and 5. Next, 2 to 6. Different variables and different classes. We can construct 2 to 6. So from 2 it is finished. Next, 3. So 3 to 1, 3 to 2 will not be constructed. Why? Because same class. Next, 3 to 4. So different variables, different classes will be constructing. Next, 3 to 5 also will be constructing. So 3 to 6. 3 to 6. Can we construct? Both belongs to same variable. Classes are different, but both belongs to same variable. So if one condition is false, means will not be constructed. So 3 to 6, no edge. Next, starting from 4. 4. So we cannot construct with 1. Why? Because same variable. So 4 to 2 is already there, 4 to 3 is already there. Next, 4 to 5, 4 to 6. Can we construct 4 to 5, 4 to 6? Can anyone type it in the chat box? 4 to 5 and 4 to 6. Can we construct edge between 4 to 5, 4 to 6? No. Good. So why? Because 4 and 5 belongs to same class. 4 and 6 also belongs to same class. Same class. Next, with 5. So 5 to 1 is already there. We cannot construct 5 to 2. Why? Because the same variable. 5 to 3 is already there. So we cannot construct 5 to 4 and 5 to 6 because same class. Next, starting with 1. So 6 to 1 is already there. Next, 6 to 2 is already there. So 6 to 3, we cannot construct same variable. So 6 to 4 and 6 to 5, we cannot construct same class. So this completes the graph construction. This completes the graph construction. Now type it in the chat box if you have any doubts. So otherwise we'll check whether the graph has click of size at least k or not. K or not. Type it in the chat box if you have any doubts or if you have understood. Type it in the chat box, then I will go for the finding the click size for this graph. Okay. So now we have to find the click size for this one. So all of you note down this graph in your book, it will be useful. So next, so we have to find the click. So before finding the click, again I am drawing the same graph. So this is the graph we got from the formula. So now we have to find the click for this graph. Click is nothing but the maximal complete subgraph. Complete subgraph. So subgraph, that's why I'm starting with the any 5 vertices. Any 5 vertices. And we will be checking whether that subgraph is complete or not. Complete or not. Any 5. You can take any 5 vertices. So I'm starting with 1, 2, 1, 2, 4, 5, 6. 1, 2, 4, 5, and 6. So in the graph, 1 to 5 edge is there, 1 to 6 edge is there. Next, 2 to 4 is there, 2 to 6 is there, 2 to 6 is there. So is this graph complete? Can anyone tell in the chart box? You can take any 5 vertices and check whether that graph is complete or not. Complete or not. Complete means it should contain at least one cycle, or every pair of vertices should have an edge. So if you take 4 to 5, no edge, or 4 to 6, no edge, 5 to 6, no edge. So if 4 to 5, 5 to 6 edge is there, then that will be 1, 5, 6 will be one subgraph. No. No. So this, if you take any 5 vertices, it will not be complete. It will not be complete. So you can try with other possibilities also. I am taking only one possibility. So you try with other possibilities also. If you take any 5 vertices, it will be incomplete only. That is not complete. So next, we will be taking any 4 vertices. We will be considering any 4 vertices. Any 4 vertices. Any 4. And we'll be checking whether it is complete or not. Whether it is complete or not. Any 4. I'm taking 1, 3, next 4, 6. 1, 3, 4, 6. 1 to 6 edge is there. Next 3 to 4 edge is there. So is this second example complete? Not only this one, you can take 1, 2, 4, 6. So 1 to 6 is there, 2 to 4 is there, and 2 to 6 is there. Is it complete? Is it complete? Any 4 vertices. So it is also not complete. It is also not complete. Next, any 3 vertices. Any 3 vertices. Next, we will be considering the any 3 vertices. So 1, 5, 6. There is an edge. I am taking 1, 5, 6. So 1 to 5 edge is there. 1 to 6 edge is there. 1 to 6 edge is there. Next, you can take 2, 4, 6. 2, 4, 6. Another combination. Is it complete? Any 3 vertices in the graph. If you take any 3 vertices in the graph, is it complete? No. 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 Next, any 2 vertices. Any 2 vertices. Any 2 vertices. So any 2 vertices means, so we can take 1, 5, 2, 4, or 1, 6, 1 6 or 2 6, 3 4, 3 5 like that. So 1 2 5, 1 2 5. This is one combination. 1 2 6. This is another combination like this. 2 4. This is one combination. Next 2 6. This is another combination. Similarly 3 4 3 5. You can take. You can take. So two vertices. Is it complete or not? So two vertices are there and there is an edge between those two vertices. So and it is a undirected graph. That means 1 to 2 edge is there, 5 to 1 also edge is there. 5 to 1 also edge is there. So it is complete. Complete. Now check once. So two vertices is complete. Why? Because so here whatever the edges we are taking, it is an this graph is an undirected graph. 1 to 4 edge is there means 4 to 1 also edge contains. So here if you see 5 vertices. So here some in between the pair of vertices some edges are not there. That's why if you take any 5 vertices it is not complete. Why? Because so the graph, the subgraph doesn't contain any loop. If you take 4 vertices also, it is not complete, no loop. 3 vertices also, no loop. But if you take 2 vertices, 1 to 5, 1 to 6, 2 to 4, 2 to 6, it is complete. Why? Because 1 and 5, there is edge in the graph. So 1 to 5 is nothing but 5 to 1 also. 5 to 1 also. So 2 vertices is complete. So if we take 1 comma 4, then there is no edge. No edge. So we'll not be taking the 1 4. Why? Because the given graph doesn't contain 1 to 4 edge. No. That's why we'll not be considering those two vertices. We'll not be considering those two vertices. So here in 5 vertices graph. So 5 vertices graph. See here we have taken 1, 2, 4, 5, 6. Why we have taken these vertices? So from 1 to 5 there is edge. 1 to 6 there is edge. So we have taken 4. 1 to 4 there is no edge. But 2 to 4 edge is there, no? That's why we have taken 4 here. We have taken 4 here. Similarly, in 4 vertices graph. So I have taken 1, 3, 4, 6. 1 to 6 edge is there in the graph. 3 to 4 edge is there in the graph. So one pair should contain edge. At least one pair should contain edge. So if the graph doesn't contain edge, then how the subgraph will contain edge? That's why here in 2 vertices, we'll be taking the vertices only those vertices having edge in the graph. 1 5, 1 6, 2 4, 2 6, 3 4, 3 5, 3 5. So 2 vertices is satisfied. 2 vertices is satisfied. So in order to satisfy the theorem, so what is the condition? Click size must be at least k. At least k. So what is the click size we got? 2 greater than or equal to. How many classes are there in the formula? 2. So 2 greater than or equal to 2. Condition is true or false? 2 greater than or equal to 2. Condition is true or false? Condition is true. True greater than or equal to true. Condition is true. So therefore, the theorem is satisfied. Satisfiability reduces click tension problem. This theorem is satisfied. So how the theorem is satisfied means whatever the formula we have taken that is evaluated to true. So that's why the graph has a click size at least k. At least k. So now so from Cook's theorem, we'll be taking one statement. We'll be taking one statement. That is nothing but satisfiability satisfiability reduces to CNF satisfiability. Don't get confused. Satisfiability means we'll be taking formula. That formula can be either in CNF or DNF. CNF satisfiability means we'll be taking the formula which is in conjunctive normal form. That means in between the clauses the symbol should be and in each clause. So in between the literals the symbol should be R. That's all. So we'll be taking one statement from Cook's theorem, that is satisfiability reduces CNF satisfiability. So this is equation 2. Equation 2. So apply transitivity. Apply transitivity to equation 2 and equation 1. Equation 2 is satisfiability reduces CNF satisfiability. What is equation 1? Theorem statement. What is the theorem statement? CNF satisfiability reduces to Click-Decision problem. Click-Decision problem. So if we apply transitivity to both the equations, then we will get the satisfiability reduces. Satisfiability reduces to Click-Decision problem. Click-Decision problem. If the condition is satisfied, therefore Click-Decision problem is NP-hard. If this condition is satisfied, then we can say that the problem is NP-hard. 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 So if you understand the problem, it will not be as tough as you are thinking. Just how to prove the problem is NP-hard means just we have to satisfy the theorem. Theorem is nothing but we have to take one formula. For that formula, we have to construct a graph, and for that graph, if it has click-off size at least k, then the theorem will be satisfied. If the theorem is satisfied, then we'll be taking one statement from Cook's theorem and applying transitivity to both the theorem statement and Cook's theorem statement. Then we'll be getting satisfiability reduces the Click-Decision problem. Click-Decision problem. So if the condition is satisfied, then we can say that the problem is NP-hard. NP-hard. So here the problem is Click-Decision problem. Decision problem belongs to NP. CDP belongs to NP. So if the problem is NP-hard and it belongs to NP means, so it is also CDP is also NP complete. NP complete. Now type it in the chat box. So if you have understood, or once again you want to explain me. So now I will take one formula. So which evaluates to false. And after constructing the graph, it will not contain click-off size at least k. So then you will be clearly understanding. So now I will take another formula. So I am going for the next example. For same Click-Decision problem only. Example. So f equal to x1 or x2 and x1 bar or x2 bar and x1 bar or x2. So here this formula contains three classes C1, C2, C3. K equal to 3. K equal to 3. K equal to 3. So I am taking x1 equal to true. X1 bar will be false. Next, x2 is false. X2 bar equal to true. Check whether this formula evaluates to true or false. Evaluates to true or false. So C1. So x1 value is true or x2 value is false. So totality is true. C2. So C2 is x1 bar false or x2 bar true. So it is false. Next C3. So x1 bar false or x2 is false. So it is false. Now F equal to C1 value is true and C2 is true. C2 is true and C3 value is false. So it is false. So one false is there means it is false. So C3, x1 bar value is false, x2 is also false. False or false means false. So one class is false means the entire formula will be false. Why? Because in between the classes the symbol used is and. So we will be getting the false only. False only. So if you are getting false means the graph will not contain split of size at least 3. At least 3. So now we'll see whether it contains at least 3 or not. 3 or not. So here it contains 3 classes, no? C1, C2, C3. So K equal to 3. So left side I am taking 2 dots. 2 dots. Why? Because the first class contains only two literals. First one is x1, comma 1. First vertex. Second vertex. What is the second literal in the first class? x2, comma 1. Next, middle. So C2 contains 2 letters. That's why 2. That's why I am writing 2 dots. So x1 bar comma 2. Second one x2 bar comma 2. So this is third vertex and this one is fourth vertex. Next, right side. Third class contains 2 literals. So x1 bar comma 3. Next x2 comma 3. So 5, 6. So now the graph G has 6 vertices. 6 vertices. So total 3 classes. Each class contains 2 letters. That's why 1, 2. Next 3, 4. Next 5, 6. 5, 6. Now next we have to construct edges. Can we construct 1 and 2? No, same class. 1, 3? No, same variable. So we can construct between 1, 4. 1 to 4 we can construct. We can construct 1 to 4. 1 to 4. Next, can we construct 1, 5? No. No. Why? Because same variable. X1 bar belongs to same variable. 1 to 6. So different classes, different variables. We can construct 1 to 6. 1 to 6. Next, starting with 2. So we cannot construct 2 to 1. So we can construct 2 to 3. So we can construct 2 to 3. We cannot not construct 2 to 4. Why? Because of same variable. Same variable. Next, can we construct 2 to 5? Yes, we can construct. Why? Because of different classes, different variables. We can construct 2 to 5. Next, can we construct 2 to 6? No, same variable. X2, X2, same variable. Classes are different, but it belongs to same variable. Next, so 3 to 1, no. 3 to 2 already there. 3 to 4, we can construct. 3 to 4, no. Why? Because of same class. 3 to 5, no. 3 to 6, 3 to 6, we can construct. We can construct. Why? Because different variables, different classes. Next, starting with 4. So 4 to 1 is already there. 4 to 2 we cannot construct. 4 to 3 also we cannot construct. 4 to 5. 4 to 5. Can we construct? We can construct. 4 to 5 we can construct. Different variables, different classes. So 4 to 6. No. Why? Because x2 bar, x2 belongs to same variable. So we cannot construct. Next, 5 it is completed, 6 also it is completed. So now we need to check whether it has click of size at least 3 or not. So first we will be taking the subgraph. So any 5 vertices, any 5 vertices, any 5 vertices, any 5 vertices. If you take, see here, 1 degree is 2, 2 degrees also 2, 3 degrees also 2, 4 degrees also 2, 5 degrees also 2, 6 degrees also 2. Every vertex is having the degree of 2. That means you can take any 5 vertices, any 5 vertices, either 1, 2, 3, 4, 5 or 1, 2, 1, 2, 4, 5, 6. Let us see. 1, 2, 4, 5 and 6 and 6. So 1 to 4 edge is there. 1 to 4 edge is there. 1 to 6 edge is there in the graph. Next, 1 to 5 no edge. 1 to 6 edge is there. Next, starting with the 2. So 2 to 4 no edge. 2 to 5 edge is there. 2 to 6 no edge. 2 to 6 no edge. So 2 to 4 no edge. 2 to 5 edge is there. That means if you take any 5 vertices, it will not be complete. You can check. You can check. Next, any 4 vertices. Any 4 vertices. So here all the vertices having same degree. So you can consider any 4 vertices. Any 4 vertices. If you consider 4 vertices, 1, 3, left side I am writing 1, 3. Right side I am writing the 4, 6. 4, 6. We'll check. So 1 to 4 edge is there. 1 to 6 edge is there. 1 to 6 edge is there. Next, 3 with 3. So 3 to 6 edge is there. 3 to 6 edge is there. And 3 to 2 edge. So is it complete? No. If you take any 4 vertices, again it will not be complete. Again it will not be complete. Next, any 3 vertices. Any 3 vertices. If you consider any 3 vertices, any 3 vertices, if you take 1, so 1 to 4 edge is there, 1 to 6 edge is there. If you take 1, 4, 6. 1 to 4, 1 to 6. So 4 to 6, no edge is there. That's why it's not complete. So if you take any 3 vertices, it will not be complete. It will not be complete. So if you take any 2 vertices, then it will be complete. Then it will be complete. That means, so if you take 1, 4, so edge is there. 1, 6, edge is there. So next, 2, 3, edge is there. 2, 5, edge is there. 3, 6, edge is there. Next, 3, 6, edge is there. Next, 4, 5, edge is there. Like that. So if you take any 2 vertices, it will be complete. Any 2 vertices, it will be complete. Two vertices, it is complete. It is complete. But here number of classes is 3. 3. So if you go to the theorem statement, so click must have size of at least k. Click size must be at least k. Click size at least k. At least k. So here what is the click size? 2. Greater than or equal to. What is k? Number of classes in the formula. What is the number of classes in the formula? K equal to 3. 2 greater than or equal to 3. Condition is true or false? Condition is false. Condition is false. That's why if the formula evaluates to false, if the formula evaluates to false, if the formula is evaluating to false, then we cannot satisfy the theorem. We cannot satisfy the theorem. So here this formula is evaluating to false. That's why it doesn't contain the tick size at least k. At least k. Have understood the second example and first example. The first example is evaluating to true. That's why it has a click of size at least k. But the second example is evaluating to false. That's why it doesn't have click of size at least k. So you can try with some other examples. Have understood, Amma? Type it in the chat box. So if you have understood, then in the next class we'll go for the next one. That is a node cover decision problem. Node cover decision problem. Subara sir. Subara sir. Subara sir.
మేడం హలో
Madam ki Radha madam already పంపించాను. 4 questions.
మేడం whole question.
Okay na sir?
మేడం ఎస్ మేడం క్వశ్చన్స్ ఇచ్చి
My students wait for poll questions. So after completing poll questions, you can leave the session.
Subara sir, Subara sir,